Okay, so let's start. Good evening, everyone. I am Harshit Agrawal. Welcome to the sixth live session of mine for the week 6 of the course Structural Dynamics CE07. I hope I am audible to everyone. Yeah. So, in today's session, we will cover following things. First, we will just review what was covered last week, that is in week 5 of this course. Then we will see what was taught in week 6, a brief overview just to brush up the content and get everyone on the same level. Followed by a series of two questions, each one different from the other, based on the content covered in week 6 and assignment 6. I'll first explain you the question and then step by step we will solve the question. So make sure you all have a pen and a paper beside you so that you can solve along with me. Finally, we will go into additional learning wherein I will present a tutorial on MATLAB coding for the content covered this week. So just like in the past sessions of mine, I will step by step guide you how to code in MATLAB and we will see the results. So if you have access to MATLAB, just keep it open in your laptop or PC. Else just write the syntax along with me and try to replicate it later on. And if any doubts, can ask me in the next live session. So I hope everyone are clear with the instructions. If you have any doubts, can raise a hand or write your query in the chat box. I will respond as soon as I will see. Okay, so let's start. So during the week 5 of the course structural dynamics, we learned about various numerical methods to solve an ordinary differential equation for a single degree of freedom system. Now, what are numerical methods? They are just iterative based techniques wherein previous and post response or previous or initial response of a structure is used to compute ahead responses. So in numerical method, we learned about three different methods based on interpolation of excitation function, wherein function is deconvoluted into simpler form for estimation for estimating individual responses and then summed up again at the end. Then there is a central difference method wherein pre and post deformation response is used to estimate all kind of responses. And finally, there is Newmark's method wherein certain functions and assumptions helps us to iteratively estimate the response of a system. Now, recall all these methods. These all methods work effectively when our arbitrary function is complex and can't be solved by any other previously learned methods. So that's what make numerical method a important technique. Now, last week we saw couple of MATLAB tutorials, wherein first was for a single degree of freedom system subjected to blast loading, and in figures you can see how we got responses and how time step or delta t chosen at the start of chosen at the start played an important role in obtaining accurate responses. So you can see in the figures, as the delta t value as we decrease the delta t value, we obtained a much smoother curve and a much closer representative of actual response of the structure. And this was for a damped single degree of freedom system subjected to earthquake ground motion, and we can see how amplitude of vibration is dying off with time. So this was what we covered last week in week 5. Now in last week, that is in week 6, we went on to learn about response spectra. That is nothing but maximum response of a single degree of freedom system subjected to earthquake ground motion. Now why we are calling it a spectra? Because for different damping coefficient and different period of vibration, we estimate maximum response and thus plot in a single plot to make it a response spectra. The content of week 6 was divided into different modules. As in week 6 module 1, we learned about basics of response spectrum, what it is, how to construct it, and where it finds it as significance. In week 6 module 2, we learned about special cases of response spectrum, based on damping and stiffness of the system. And in module 3, that is the final module of week 6, we learned about tripartite plot. Tri- Tripartite plot. What it is, how to make it, and how to read it. So moving ahead, we'll just brush up all the formula and relationships we saw this week so that everyone can understand numerical and MATLAB part coming ahead properly. So just to brush up the basics, the dynamic equilibrium equation is given as inertia force plus dynamic force plus stiffness force is equal to externally applied force. And assuming that the frame is rigid and deflection can happen only in the horizontal direction and the mass of the supporting columns is negligible, the actual frame structure can be transformed into an analytical model as shown in the figure. Now, this is something we have been reading since week 1 of this course. Now we understand from the discussion we had a couple of slides back what a response spectrum means. But there are several key points to remember about response spectrum. So, first is that the maximum response depends only on the natural frequency and damping and this is irrespective of the mass and the stiffness of the system. This we saw last week. Second, in slow vibrations, tall buildings are affected, and in fast vibrations, small buildings are affected. Why? Because of resonant frequency. So, if we assume same stiffness for tall building, mass will be more, so natural frequency will be less. Hence, at small vibration, resonant condition might be achieved, and this is why at slow vibration, tall buildings are affected, and vice versa for the small buildings. And then we saw how to construct response spectrum. This can be done by estimating maximum response of a single degree of freedom system as a function of time period. The basics of this we will see today in MATLAB tutorial also, and where it find and MATLAB tutorial also, and we'll see the response of the system for the deformation, velocity, and acceleration. And finally, where we find the application of response spectrum, it is in the earthquake designing. So, on upon averaging a response spectra for various damping coefficient, it we can design a earthquake resistance structure. How? By calculating the base shear and the base moment. This is also we will see today in one of the numerical. Now, there are several special cases of response spectra. First is zero damping, in which spectral acceleration is equal to pseudo-spectral acceleration. This we saw in the week content. Second is the stiff system. In a stiff system, what happens upon vibration? System doesn't deform because it is very stiff and and moves along with the ground. Hence, the spectral displacement, spectral deformation, and spectral velocity are approximately zero. Why? Because they are relative. They are relative terms, and spectral acceleration is approximately equal to the maximum ground motion. And final case was for flexible system. So what happens here, upon vibration, when ground moves rapidly, the heavy mass doesn't get the chance to move since it is very flexible, and hence the absolute acceleration remains almost zero. But the spectral deformation and spectral velocity are almost equal to the maximum ground displacement and maximum ground velocity respectively. So this was different special cases of response spectrum that we read this in week 6. And finally, we s- we read about tripartite plot. So what is a tripartite plot? It is a graph that shows all displacement, velocity, and acceleration response in a single plot. How it is possible? So if we know the spectral deformation, then pseudospectral velocity and pseudospectral acceleration can be determined by the following relationships. So thus taking natural period on x-axis and the pseudo spectral velocity on y-axis, PSA lines can be constructed as a positive slopes of 45 degree, and spectral deformation lines can be constructed with a negative slope of 45 degree. Thus, if we know the natural period, we can determine PSV, and then by dropping perpendiculars, we can determine PSA and SD. Okay. So suppose this is a tripartite plot. and we know the natural period. So from the known natural period, we can first determine the pseudo spectral velocity, and then by dropping perpendicular on the displacement line, we can determine the spectral displacement, and then by dropping the perpendicular on acceleration line, we can determine the spectral acceleration. So I hope that weak content is clear to everyone. Any doubts in what was taught this in week 6? Okay, so let's proceed ahead with the first question. So this is the first question. A structure model at a single degree of freedom system has a natural period of 1 second. Use the response spectrum method to determine the maximum absolute acceleration, the maximum relative displacement, and maximum relative pseudo velocity for a foundation motion a foundation motion equal to ns component of an El Centro earthquake of 1940, and b the design spectra earthquake with the maximum ground acceleration equal to 0.32 g. Assume 10% critical damping. So the response spectrum for these two cases will be given to you, that I will show in the next slides. So I will wait for a couple of minutes for you to read the question and think what will be done in this question, and then we'll proceed ahead. Yes, Mr. Upadhyay. You can write your query in the chat box if you have any doubt.
Oh, sir.
Yeah,
Yeah, we are having, if we are having the graph,
yeah,
then for a particular value of that natural period and a particular value of critical damping,
yeah,
we can find what is the displacement and what is the pseudo velocity and pseudo acceleration.
yes,
And if that acceleration is to be with some peak value like 0.3 g or something like that,
yeah,
we have to again convert it into that way.
yeah. That is what we
Will
will
it
do
be
in this
okay?
question ahead. I will just start the solution so you can
Okay.
see the things.
Okay. Okay. My answer is correct, no, sir?
Yeah, 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 you are correct.
Okay. Thank you, sir. Thank you.
So, what was given in the question? We know the natural period and we know that critical damping. And there are two cases of response spectrum. First is El Centro earthquake of 1940, and second is the design Spectra earthquake. Okay. So, this is what given in the question. So, this is a representation of El Centro earthquake of 1940. This is a response spectra for this. So we know the time period is 1 second. So we'll drop a perpendicular from 1 second to the graph of our interest. So this is the graph for damping coefficient of 10%. Okay. Now at the intersection of this graph, we will first get the value of spectral velocity, which is coming out to be around 20 inch per second. And then dropping the perpendicular on the acceleration line, we can find the pseudo spectral acceleration, and dropping the perpendicular on the displacement line, we can find the spectral displacement. So these are the values that are coming from the tripartite plot. So this was for the first case. Now second case was basic design spectra, which is shown in the figure. Now, in this again, the x-axis is frequency, but we know the time period. So frequency is nothing but 1 upon time period. So again, it will be 1 only for us in this case. And the damping coefficient is 10%. So again, you need to see the damping coefficient, which damping coefficient we are in interest of, and we can calculate the velocity. And in this case, the displacement line and the acceleration line are represented in a different way. So here only you can read the displacement to be around close to 10 inch, and the acceleration would be close to 1. So you can see this is how this graph will be read. But you can see in the bottom it is written that this is a basic design spectra normalized to peak ground acceleration of 1 g, but in the question we were given it is 0.32 g, so we need to scale the values. So how we can scale the values? Just multiply by the factor 0.32 upon 1, so we will get the actual responses of velocity, acceleration and distance. So I hope everyone are clear with how to read the response spectra, and and how to take care of what was asked from us. Any doubt in this question? Yeah, say Upadhyay.
Sir, in earlier graph, I understood that it is perpendicular in two different directions.
Yeah,
That velocity, the acceleration and displacement.
yeah.
But in this diagram, I'm not
See
understanding
the
how.
values, how the values are represented here. So the values are along this line only where we found the interaction. So that's why I didn't drop the perpendicular. You can read the values from here only. So one more perpendicular could have been dropped for acceleration at this line,
Okay.
but the displacement value is here only, so that's why I didn't drop that perpendicular. So
Uh,
displacement
Understood.
is here
Yeah.
only,
Yes.
and acceleration we can see by dropping a perpendicular here.
Yes, sir. Yes, sir. Thank you, sir. Thank you.
Okay, clear.
Yes, sir. Clear. Thank you, sir.
Okay, so now we'll see the next question. This was one basic question where we saw how we read tripartite plot and how to interpret the values. Now this is the second question. A water tank is supported on a cantilever tower of height 25 meter as shown in figure. The total weight of the water tank, including the weight of the water and the self weight of the tank, is 45,000 kg. The stiffness of the water tank is equal to 700 kilonewton per meter. Assume a damping of 2%. The water tank is to be designed for El Centro ground motion characterized by response spectrum. This El Centro earthquake motion we saw in the last question also. So determine the maximum deformation and maximum base shear and base moment generated in the tank. So I will wait for a couple of minutes for you to think how to proceed on with this question, how to first define the parameters that we need, and then how we'll proceed on, and then I will share the solution. Yes, Upadhyay.
Yes, sir. It is given that k and mass is given,
Yeah,
so we can find the natural frequency,
yeah,
and then we can find what is natural period.
yeah.
And with natural period and this thing, the damping ratio,
Hmm.
again referring to that graph, we can go for finding the acceleration.
Yeah.
And if we multiplied mass into acceleration, we'll be getting what is the force being developed, and that will be base shear. And if we multiply it by height of that water tank, we'll be getting the bending moment at the base. That way we can go for.
Partially you are correct. Partially I will.
I'm not understanding what is written at bottom. UG double dot is point 0.5 something.
That is just a representation. You don't need to care about that.
Okay, okay.
Partially you are correct, but the maximum base share and moment generator is determined by other relationships. So that I will tell in the solution. Okay.
No. Yes, thank you, sir.
So let's see the solution. We know the height of the tower, we know the weight of the tank, and we know the stiffness of the column and the damping present in the system. Okay. So the first step, as always, I told in the previous sessions also, is to determine the system parameters. So what system parameters we need to determine? First is the natural frequency. So what is natural frequency? It is nothing but under root of k by m. So K is known to us, mass is known to us. So omega n will come out to be 3.94 radian per second. And if we know the natural frequency, natural period is nothing but 2 pi by omega n. So it will come out to be 1.6 seconds. So this is the natural period. Now, knowing the natural period and the damping coefficient, we know the El Centro earthquake. So suppose 1.6 is lying somewhere here, and we know this is the curve for 2% damping coefficient. We can easily determine the spectral velocity, the spectral acceleration, and spectral displacement. So these value will come out to be 25 inch per second, 0.28 G, and 6.2 inches. Okay. So what is the maximum deformation now? The maximum deformation will be nothing but the spectral distance deformation that we are getting, which is 6.2 inches. And if we convert inch into meter, it will come out to be 0.157 meter. Okay, so this is the maximum deformation. Now we need to determine the maximum base shear and base moment generated. So the maximum base shear is given by nothing but k times maximum deformation. So Vmax at base is nothing but the stiffness of the column and the deformation in the column at the top. So it is like a fixed from one end and free from other end. So we know how much displacement is occurring at the free end, and we know the stiffness of the column. So we can determine the maximum shear force generated at the base by K times U naught. So K we know, U naught we know. So maximum base shear will come out to be 109.9 kilonewton. Okay. And thus maximum moment will be nothing but base shear generated into height, and it will come out to be 2747.5 kilonewton meter. So this is how we determine the maximum base shear and base moment. So Ku naught is nothing but force acting at the top. And if we consider the system to be in equilibrium, the same shear force should act at the bottom also. That's why the maximum shear force at the base is nothing but K times U naught. And then moment we can easily estimate by Vmax into L. So I hope this part is clear now. How to read the tripartite plot and how to interpret value and how to determine maximum base shear and base moment.
Yes, sir. Very, very clear, sir. Thank
Okay.
you, sir.
Okay. So now as a part of additional learning, in every live session of mine, I cover a tutorial on MATLAB wherein I will describe a single degree of freedom system covered in the week content. So for week 6, our objective is to calculate the elastic response spectra in terms of spectral displacement, spectral velocity, and spectral acceleration for any prescribed time acceleration seismic excitation, and the response is calculated in a specified range of frequency or period using Newmark's method. So for this tutorial, let's assume an earthquake ground motion of 0.5 g, damping coefficient to be 10%, and mass of the system to be unity. Okay, so now I will open my MATLAB software in the laptop. You can see how to code as of now and implement the same later on. We will go step by step and define everything properly and clearly. All the syntax that I will be using today are little complex than the last time, but most of the things have been covered in the previous tutorials also. So you just need to pay attention. I will try to clarify all of them with time, but try to learn more about them from MATLAB official webpage. And the more you will practice, the more clarity and command you will gain over these things. Okay, so let's start with the MATLAB part. So first, we need to define the given values. So what all values are given to us? Mass of the system is unity. Acceleration of ground is zero point 0.5 g. So g is nothing but 9.8, and damping present in the system is zero point 0.1. Okay, so these are the values that are given to us. Now we need to define the time related parameters. So what are the time related parameters? Since we need to make a response spectra, we need to first define what range of time period we need to look for. So let's say we are looking for different time periods ranging from 0 to 25 second at an interval of zero point 0.1. So after every point, like the time period will be 0, zero point 0.1, zero point 0.2, zero point 0.3 up till 25 seconds. Okay. So for all these different time period, we will estimate the maximum deformation, maximum velocity, and maximum acceleration. Okay. And let's define a parameter tt, which is length of t. This will help us when we'll create loops. Okay. Now for each time period, we need to have a time interval in which we are getting the response, and from those responses we will estimate the maximum deformation for a particular time period. So let's define delta t as 0.01 second. This is something that we did in the last tutorial also. So now whatever we are defining, this is for a particular time period, and the t that we have defined before is a different ranges of time period in which we will do repeated calculation. Okay, so let's define delta t as 0.01, and t is nothing but for how much interval in each time period will uh, get the response. Okay, when I will proceed on ahead in the loop partner, you will understand like what we are doing. Okay, so the first time period parameter, this is time period of the structure, and this is for each time period for how much time we are observing. Okay, so let's keep this as up to 50 at least, because the maximum time period will be 25. So time of observation should be greater than that only, should be at least greater than that. Okay, so let's now proceed on with the estimation. You can see in the workspace part how each parameter we are defining are getting stored. So this t is time period, and this t is how much values we will look at for each time period in using Newmark's method. So now we'll move on with the estimation. So we'll first create a loop for j equal to 1 to tt. What this loop is doing, we are looping over for each time period right now for this. So for a particular time period, we will define all the remaining parameters. We will apply Newmark's method for this time range. We will get the velocity, displacement, and acceleration responses, and from those responses we'll get the maximum response for that time period. We will store it in another vector, and then we'll move on with the next time period. So again we'll do the same thing for the next time period, and this is how we'll get the maximum deformation for each time period, and finally we will create a plot from this. So this is the first loop. So for j is equal to 1 to tt, let omega, so we know the time period. So first we need to find the value of omega. Omega j comma 1. For first, for any time period tj, omega will be given by 2 pi by t of j. So what is t of j here? So if j is equal to 0, the time period is 0, so omega will be infinity. For time period is equal to 0. 0.1, we will calculate omega by 2 pi by 0. 0.1, then 2 pi by 0. 0.2 till 2 pi by 25. So this is how this time we need to estimate these parameters for each time period. So omega will be defined by this. K will be nothing but omega square into m. So omega is under root of k by m, so k will be omega square into m. So omega of j square times m. And C, the damping coefficient is nothing but 2, the critical damping factor is nothing but 2m omega j times xi. So these all relationships we know from the previous lectures. So this is how we have first determined the required parameters. Now we'll move on with the linear acceleration method. What is linear acceleration method? Newmark's method. So in Newmark, there are two types of methods, na? Linear acceleration and I guess average acceleration. So we are using linear acceleration. So for linear acceleration method, gamma is taken as 1 by 2 and beta is taken as 1 by 6. This we saw in the last week also. So first we'll define the initial condition of the system. So let initial velocity, initial displacement, and initial acceleration of the system to be 0. So Once we have defined these values, we need to calculate the parameters that we require in Newmark's method. So what all parameters we require? There is one k bar, and we know k bar into u is equal to p bar. So for p bar, we need to estimate a and b. So you can see this relationship from the last week content also. I remember those relationships. I am just writing those relationship directly. So k bar is given by k plus gamma times c divided by beta delta t plus m upon beta delta t square. Okay, so this is k bar. A is defined by m upon beta delta t plus gamma c divided by beta, and A is defined by m upon 2 beta plus delta c delta t into c into 0.5 gamma on beta minus 1. Okay, so these are the values of k, a, and b. So let initial velocity displacement is u naught. Initial velocity is defined by v naught, and initial acceleration is defined by a. So these were parameters defined for each time period. So these parameter will change when the time period will change. Why? Because k value will change. Okay. So these parameter will change as the time period will change. Now within each time period, we will loop over each time step dt for t. So we have defined that in each time period, we'll see the response for 50 seconds with these conditions. So now we'll make a loop for that. Okay, so for I is equal to 1 to length of t minus 1, df is nothing but minus g times ag. Okay, so this is the force that is remaining constant, and now we need to create the Newmark's function. Okay, so the function is the same that we defined last week also. So I will again just I have that function stored in my system, so you can just see the function how we define the function. So we need output of t, u, v, and a, and what all inputs we need to give it to the function: t, a, b, df, dt, k bar, u naught, v naught, a naught, gamma, and beta. So all these values we have defined previously before the loop. Okay. So based on this value, first df bar will be calculated using this relationship. This we saw in the last week also. Then du will be estimated. That is change in displacement, the change of deformation. Then change in velocity will be estimated, and then change in acceleration will be estimated. So once du dot and du double dot is estimated, you can like the next deformation is nothing but u naught plus du. The next velocity is nothing but v naught plus du dot, and next acceleration is nothing but a naught plus du double dot, and the time will also be appended by delta t. So we will just call this function t comma u comma b comma a is the response that we found from the function is nothing but Newmark d a b df dt. You can see in the help bar it is showing us how many parameters we want to define, how what all parameters we want to define, gamma and beta. So these all values we have calculated initially only. See, this is u naught, v naught, a naught, k bar, a, b, t is defined initially only, df we have defined here, gamma and beta we also defined initially. So this is how we will call the Newmark function. Okay. Now, once the we get the response of u, v, and a, we need to store those responses first. So, how we'll store the responses? We'll define new parameters. So, u of t1, see, let's say this is the name that we are calling is nothing but this. So, we saw how we write this syntax in the last class. Then v of t1. So we'll get like from the function, we will get a range of values when this for loop will complete it. So we are storing those values here in a matrix so that later on we can compute the maximum. Okay. Remember, this is for one time period. Okay. So once we have stored the values, we need to append the u naught, v naught, and a naught value again. So we need to set up initial values again for next loop. So how we set up initial values for next loop? U naught will be appended to u, v naught will be appended to v, a naught will be appended to a, and t is nothing but t only because t is appended here only. Okay. So this is how the inner loop will end. So this is the loop for estimating response for a particular time period using Newmark's method. Now, once we have the data stored for a particular time period, we need to get the response, spectral response. So spectral response is nothing but maximum of this, maximum of this, and maximum of this for that time period. So what we need to do now? Estimation of maximum values for given period. So how it is done? Umax is nothing but absolute of, no, maximum of absolute of u of t1, Vmax is nothing but maximum of absolute of v of t1, and Amax is nothing but maximum of absolute of v of t1. Okay. So once the maximum values are stored, again we need to store this. These maximum values are nothing but spectral displacement, spectral velocity, and spectral acceleration corresponding to a particular time period. So we'll store these values in another vector that is defined by SD, SV, and SV, SPV, and SPA, and this will store maximum responses for each time period. So SD is this, SPV is nothing but, we saw this relation SD times omega. So we saw this relation earlier also, and spectral acceleration is nothing but SD spectral displacement times omega square divided by G times G. So if you want spectral acceleration in terms of 2.4 G or something, so we will divide by this. And the next time period will be nothing but Tj comma 1 plus what was the delta t that we took for time period 0.1. So this is the next time period. So this is how we'll end the initial loop. So if there is no error in the calculation or no error in anywhere, so we won't observe any message here. So this shows that the code that we have written is correct. Okay, now what we need to do, we just need to append the initial spectral displacement values to 0. Why? Because we initially took time period of 0, which will yield omega as infinity and will cause error in the graph. So we'll just append the initial value to be 0. And initial acceleration will be nothing but the ground acceleration only. Okay, so once this is done, we can create the plot. So define figure. In this figure, we'll create subplot of three rows. So in subplot 3 comma 3 comma 1, we will plot time period on x-axis and spectral acceleration on y-axis, and we will label this as, we will title this as spectral acceleration, and x label will be period, and y label will be spectral acceleration. Similarly, we will define subplot 3 comma 1 comma 2. This will be plot T comma SPV. Title will be spectral velocity. X label will be period in seconds. Y label will be SV. And finally, subplot 3 comma 1 comma 3, that will be plot of time period of and spectral displacement. So title will be spectral deformation. X label will be period in seconds. Y label will be spectral deformation. Okay, so I have defined all the three plots. Now we can see the result. So here you can see the results is not coming out to be properly. Maybe we have done something, some error in the function or somewhere, or maybe the scale of the y-axis needs to be changed. That's why the results are not coming out to be properly. So that thing I need to see later on, like how to do. There's some error in the question, I guess, somewhere. No, it is the error of the scale of the function only. So I hope you got the basic, like how to write the code. If we will remove that error of the scale, then what you will observe now, this kind of response you will observe. So you can see this is the graph for spectral acceleration, this is the graph for spectral velocity, and this is the graph for spectral deformation. So here you can see for each time period what is the maximum deformation, maximum velocity, and maximum acceleration. Now, once you know these things, you can club these three together into single plot, and that will be nothing but tripartite plot for that particular ground deformation. So I hope this tutorial was clear to everyone.